Going to continue our discussion of limits, and we'll talk about properties of limits now. So properties of limits. Okay, so we're going to assume that we have, let's take two limits. This is double S, SS. Assume that limit with x approaching a of f of x. And then we'll take another limit. So limit this L with x approaching a. Let me fix this. I don't like this. Okay, so there is an L limit, different function, g of x. They both exist. Okay, so then where number c is a real number and n is a positive integer, so we have that z with a plus. Okay, so positive integer. All right, so yeah, let's go through those properties. The first one, when I'm adding two limits, or when I'm taking a limit of a sum, so let's write sum, and we have a limit with x approaching actually a, not infinity. And we have, right, two functions being added, so f of x plus g of x. Okay, so the limit of a sum is the sum of two limits, so we can just split it into two, with x approaching a of f of x plus limit with x going to a of g of x, right? So we can take those limits, two limits separately. Yeah, so difference works the same way. Right, if I'm subtracting two functions that are under the limit, so difference. Yeah, I'm just gonna make it simple, right? You will know that if I have, let's see. All right, so if I have minus here, then right, I'll also have minus. Maybe I'll put that minus there. Okay, so if this is minus, if I'm subtracting, then this would be minus, right? Okay. So the next one is a called constant multiple. So this is property number 3. Seems like I'm doing better with writing when I have it up there. Anyway, constant multiple. So what does that mean? So again, right, so I have a limit with x approaching some number a. And this time here I have some number c, right? It was a real number. And it's multiplied by a function. So what I can do, I can take that c completely out, meaning, right, I can take that c and put it in the front of the function. Right, so let's do that. Okay, so we have that c in front of the limit. Right, it already is in front of the function. Anyway, so I have limit with x approaching a, and now, yeah, I have the function, right? So f of x. Okay, so we have that. Yeah, luckily, when I'm multiplying, when I have a limit of a product, when is it better? I think it's better when it's bigger. It's easier for me to write. Okay, so product. So what that means, I have limit of x approaching a, Now I have those two functions multiplied times g of x. Okay, so yeah, the way it works, you can just take limit of those separately, right? So that'd be limit with x approaching a, and I have f of x here. And now I'm multiplying by limit with x approaching a of g of x. Okay, so we have that quotient, so property number 5 works the same way. So, alright, so if I have a quotient of two functions under the limit, we can calculate those limits separately. Okay, this one is pretty interesting. Okay, so if I have, it is interesting, but on one hand, on the other hand, it's not. It's pretty obvious. It's pretty intuitive as well. All right, so I have this one is property number 6, power or exponent. So if we have a limit again with x approaching infinity, x approaching a, thinking about the infinity. Anyway, and then we have a function here of x to the power of n. All right, so here, what I can do here, this, right? So that exponent, that n, applies only to the function, right? It doesn't apply to the entire expression, right? It's not like this. Right, so I'm not raising the whole limit to power of n. I'm raising just that function to the power of n. Okay. So actually, it turns out it's the same as if I was raising the whole limit to that power of n. So x approaching a. Now I have that function. Okay, and yeah, I can take that exponent, that power, and put it up there. And I can do the same thing with the root. So this is property number 7, root or radical. So I have limit with x approaching a. Okay, so I have f of x here. And this is, right, here's that root. I write it as 1 over n, right? So you guys know that, let's say if I have, let me give you an example. Let's do maybe a to some power 1 over n, right? So that means, just from precalculus or algebra, right? So that n is actually the degree of the radical, right? So that n goes here. So if I was doing, say, 4 to the power of 1 over 2, right? So that 1 over 2, right? This is an exponent, right? It's not 4.5, right? You understand? All right, so that means, right? So that's the square root of 4, and that'd be 4, and that'd be 2. Okay, so 1 over n is just nth root, nth radical. All right, yeah. So let me give you an example, like how we would use those properties. I think the first couple are quite intuitive and obvious. Let me give you an example that would use maybe those couple last properties. So example 5, that's what I have in my notes, but I am not sure if it's right. So we need to calculate the limit with x approaching 1. And we have 7x to the third plus 3x squared plus 4x. How about a space? Yeah, a space. Plus 2. Okay, so what I'll do, right? First thing, I'll split this polynomial into, right, the limit of that polynomial into sum of those limits. So I'll take limit of 7x cubed. Yeah, so I'll write it carefully, right? Using just writing all the limits with what they approach, etc. Okay, so the first one will be 7x cubed. Okay, so then we have plus limit x going to 1, 3x squared, plus limit x approaching 1, 4x. This is x. And okay, the last one is just 2, right? But let's write it anyway. Approaching 1 of 2. Okay. Alright, so maybe first thing what I'll do, I'll take all those constants, right? So 7 will go here, 3 there, 4 there. And limit of 2 is just 2. Okay. Yeah, so we have 7. And now I have limit x going to 1, x cubed. Right, and then I have plus 3 limit x approaching 1, x squared, plus 4 limit x approaching 1 of x, and then I'm just going to write 2. Okay, so plus 2 limit the x approaching 1 of 2 is just 2. Okay, so now let's use that property where I can take those exponents, right? This one, and I will just put the entire limit under that exponent. So like this. So this will be 7, right? And then I have limit x approaching 1 of x. And now this whole thing is under that exponent. So similarly here, 3 limit x approaching 1 x to the power of 2. And here let's just calculate it. Okay, so yeah, I don't know, maybe in a moment I'll review those techniques of taking a limit. But basically, right, the most important and intuitive method of calculating a limit is just plugging that 1, right, into the function. So if I plug in 1, I'm getting just 1, right, out of this times 4, right? I have that 4 and plus 2. So this is 6. Okay, one more time. To take a limit, right, the most basic technique is just plug in whatever that x approaches, right? So it's approaching 1. So I'm plugging in 1. I get 1 times 4 plus 2, 6. Okay, so let's take care of the other limits. Okay, so here, again, right, so I'm plugging in 1 to the third power, it's just 1, so it's going to be 7. Right, so that first number is 7. Right, so let's do the second limit. Right, so similarly, here I'm plugging in that 1 to x, so it's 1 to the second power, still 1 plus 3 times 3, sorry. So it's plus 3, and then the last one is plus 6. Okay, so the limit is 16. Right, so I gave you that example just to show you how those properties work, because we could just we could just take that 1 and plug it in here and we would get the same thing. Okay. All right, so yeah, let's talk about this general strategy. So, you know, you may think, you could think, or the basic idea is of a limit, right? Is let's look at some little example here. What could we do? You know, let's just do like a parabola, or not like a parabola, but just a parabola. And okay, let's pick a point. Let's pick this point. Okay, so this point is 3. I don't know what kind of, and let's just make it 9. All right, so the equation of this is y equals x squared. Okay, so what this is just a regular point. It's not open circle, right? I'm trying to make it fill, but I'm not succeeding, obviously. Anyway, so if we're calculating a limit, right? So limit with, let's take x approaching 3, right, of that x squared. Right, so basically, in a sense, right, when we're taking a limit, we're evaluating the function at 3, right? So we can just take that 3 and plug it in here, right? And yeah, we just get 9, and that is it, right? So we're trying to figure out what value the value the function approaches when x is approaching 3 in this case, right? So the function is approaching 9. Okay. Let's look at another example. I don't have a graph here, but let me take it, pause the video and let me try to find the graph. Okay, so here is another example. Let's call it example 6 to make an official example. Example 6, and we need to figure out the limit. Looks like this. So limit x is going to 1, approaches 1, with x cubed minus 1 over x minus 1. Okay, so you see that the situation here is a little different. Let me show you a graph, actually. So the graph is similar to what we had above, but hold on, I don't want to mess it up, but I can always erase, right? So this is the graph. So it's also a parabola, right? Surprisingly, because we have this x cube, and you see that in this case we can't do it the same way as we did with this one, right? Because, well, I cannot plug that 1 in here. I'm getting, right, something that's undefined or indeterminate. So even though I have a regular parabola, what happens at 1 is that, right, so let's say this is my 1. The function doesn't have a value for 1. Right, so there is an open circle. So it's not really a parabola. Let me make it a different color. I mean, this is a parabola, but it's missing that little, right, that little point there. Anyway, so yeah, so we cannot do it the same way as the previous one. We cannot plug in that 1 into the function. Well, what we can do, we can just use algebra to simplify that expression, right? So I'll have limit. I hope I can fit it here. Let me move it up. Okay, let's Yeah, not that much. Okay, so we have a limit with x approaching 1. And then, right, you guys see that this x cube minus 1 is a difference of 2 cubes. Yeah, if you don't remember those formulas, look it up. X squared. So I'm factoring this, right? What I'm factoring is this, right? So x squared plus x plus 1. And then I have the... I wonder if I can erase this part. Hold on. Let me try to use this part. This. Here you go. The whole thing, huh? Okay, so let's go back. So it was somewhere here. Oh, I meant to make it shorter. Anyway, too late now. So this is x minus 1. And so those two cancel out. And I end up with limit x approaching 1. And then what I have left is x squared plus x, or plus 1 plus x. Doesn't matter. Okay, so now I can plug in that 1 into the function, right, into those two places. And I get 1 plus 1 plus 1, and that is 3. Okay, so that's the difference between finding a limit and evaluating a function. Right, so technically if I wanted to evaluate this function for 1, I would not be able to, right? So the function is undefined for 1, doesn't have value. But if I want to take a limit, right, I can do it, because when my x's are approaching 1 from both sides, the y value, right, is approaching 3. Okay, and that's what I found. Right, so that's the difference between finding a limit and evaluating a function. Anyway, so let me give you the general strategy, right? What we can do. You saw the two examples of finding a limit and using some some of those strategies that I'll try to list for you here. So general strategy. Of finding a limit. That's not right. Of finding a limit. Yeah, so the first most important strategy, right, we try to substitute the number in for x, right, in the function. So try plugging in a number. And the way I showed it to you with that x squared. Right, I don't know, I can give you another example. I have another example here, so it's always good to do a trigonometry problem. So x is approaching pi, and we have cosine of x. Right, so in this case, yeah, we can just plug in that pi. Cosine of pi is -1, and that's the answer. Right. All right. Yeah, so the second technique, second strategy, yeah, now it's right. Second technique is, right, using algebra. So use algebra. So in the previous example, I mean not this one with cosine, we factored, right? We factored the difference of cubes. So it could be factoring we could multiply, let me put it right here, multiply by conjugate, There are other techniques that I'll show you later. And then the strategy number 3, we could always graph it, right? So verify, or graph it, or use numbers, right? Just plug in some numbers that are smaller or larger, greater than that number a, right? That x approaches. Verify using graph or a table. So graph or a table. Okay. Yeah, so these are the techniques, some strategies. Let's do more examples. So this is, I believe, example 7. Or maybe we can call it 1. Example 1. And we have limit x approaching 0. And we need to take a limit of sine x over x. Okay, so again we have a situation where we can't solve it by plugging that 0 in, right? Because we get 0 over 0. Okay, so we don't have any other techniques for solving this particular problem. This one is, I think it's solved using a L'Hopital, something called L'Hopital's rule. But we can figure it out just by graphing, right? So we could look up the graph, but let me just show it to you. So if you graph it, this is 1, and that 1 gets an open circle, right? Because the function is undefined for it. So this is 1, and then the graph looks more or less like this, right? So it's a, in a sense, it's a sinusoid of like decreasing amplitude, right? So those waves are getting smaller and smaller, right? The farther I get from the y-axis. All right, so we have that open circle right there, okay, at 1. But right, it's easy to see what's happening, right? If I'm approaching 0, right, from both sides. So let me okay, I'm getting closer and closer to 0. Let me put it down here. The function gets closer and closer to 1, right? So that's actually the value of that limit, 1. Okay, so that's one example. Let me give you one more example. I give you that example with that sign, x over x, because yeah, we'll be using it later on, right? That value, that fact. Actually, we'll be using it here. The fact that sine x limit with x going to 0, sine x over x is 1. Anyway, so example 8. Alright, so let's try to figure this out. So I have a limit, let me put it here. Limit with x approaching 0 again, right? And I have 1 minus cosine x divided by x. Maybe I make it bigger, right? That's easier to write. Okay, so this is a typical example where we multiply by a conjugate, right? So when you see this 1 minus something or 1 plus, it's right, good guess, or always good to try that conjugate. So I'm multiplying by 1 plus cosine x over 1 plus cosine x, right? So I'm not changing anything, I'm multiplying that function by 1. Okay, so if I do that, right, so I have that limit, x going to 0. So the top is, right, the top will be 1 minus cosine square x. And the bottom is I have that x times 1 plus cosine. Cosine x. Okay. Yeah, so next thing we'll do, right, 1 minus cosine x squared, or cosine square x, is just sine square, right? So we have limit x approaching 0, and now we have this function here. So the top is just sine square. And the bottom, I'm just going to rewrite it. So 1 plus cosine x. Okay, so that equals, and yeah, let's continue. So now you guys see, I could take this, I could take this function, this expression, right, this one, right, and I could split it. I could take one of those sine x's, right? So sine x over x, right? And then the other sine x over this. Okay. So I will separate it, right? Based on those properties that we saw a moment ago. So I'll have two limits, right now. So I have a limit with x approaching 0. So the first one, right, is sine x over x times limit with x approaching 0. And now I have, do I remember it? Sine x. And then it's just 1 plus cosine. Cosine x. All right, so what do we have? So we know, right, we just showed that this is 1. And limit with x approaching 0 of this is 1. So 1. And now times, what do we have here? I think we can, at this point, we can plug in that 0. Right? So if I plug in 0, I get, here I get 1 plus 1. Right? Cosine of 0 is 1. So I get 2. But if I plug in that 0 in here, I'm just getting 0. So 0 over anything is still 0. So 1 times 0 is 0. All right, so yeah, that's what we have. Yeah, so we see, I wonder if I can, let me see. I want to try to figure something out. Okay, I don't know. Yeah, but then I don't know how to paste it. Anyway, right, so you guys see that this, right, limit of that equals 0. Okay. So yeah, done. This was a long section, wasn't it? So now I want to give you a bunch of problems. So practice. Try to figure them out. All right. So the first one is a limit x approaching 0. Okay, sine square x over 1 minus cosine. Okay, so that's the first problem. So the answer for this one is 2. And yeah, you need to figure it out, show work, etc. The second one, yeah, it's also limit with x approaching 0. And this time I have 1 minus cosine 2x over sine x. Okay, so for this one, you can use that identity. So cosine 2x, double angle identity, is cosine square minus sine square. Okay, so that's problem number 2. Alright, so the answer for this one is 0. Alright, so problem number 3. Okay, so we have limit x is approaching 4, and the function is a cube root of x plus 4. Okay, so the answer for this one is 2. Okay, problem number 4. So limit with x going to 2, 3 x minus 2. Okay, so this one, maybe when you're solving this one, right? So this one is, I don't think you can solve it algebraically, especially because the limit doesn't exist. Alright, so maybe make a graph for number 4. Okay, number 5. Alright, so we have limit with x approaching 0, tangent x over x. So the answer for this one is 1. Okay, number 6. Okay, so find the limit, and this time it's I'm just giving you a function. I'm looking at it at the what I have here. Okay, so we have so it's a piecewise function. So we have 5, where x is not equal to 3, sorry, and then 1, where x equals to 3. All right, so in this one, x approaches 3, right? All right, so yeah, with this one, I'm not going to give you answer for this one. Hope you can figure it out, graph it, right? There's no algebraic way to solve it, really. And number 7, again, I'm just going to give you a function, and it's this one is sine of 5x. Let me move it a little bit lower. Okay, so problem number 7. Actually, let me write it as a limit. Limit with x approaching 0. So I have sine 5x divided by x. Okay, so the answer for this one is 5. And there's a little bit of work you can show, but not much. Alright, so that's the end of that 2.1. I think. I hope. Just double check. Yeah.